Good day and welcome back for the fifth and final part of our discussion on L'Hopital's rule. So to begin, let me just note that we've been going through quite a few examples involving limits and L'Hopital's rule. And the reason we are doing this is limits will come up in multiple scenarios throughout the remainder of the semester. And I want to make sure that when we encounter limits and when we need to use L'Hopital's rule, we will hopefully have these reminders and will be quick and efficient in doing so. I also mentioned at the end of the previous video, this is a point where we would be midway through that second day of class discussing L'Hopital's rule had we been meeting in person. And I would turn the floor over to you and give you a solid 15 minutes to work through the three examples that you see on the screen. So if you haven't already spent some time thinking about these examples, pause the video and really give yourself that time to work on them. Once you've done so, we'll summarize. Now that you've spent some time working through these problems, let's begin investigating the first limit that we see. Individually, if we think about the components that make up this function, as x approaches 1 from the right, x is going to be approaching 1. In terms of 1 over 1 minus x, it's useful to visualize. 1 over 1 minus x is a rational function. It is undefined at x equals 1, where you're dividing by 0, causing this vertical asymptote. And as we approach 1 from the right, we can see that our graph is approaching minus infinity. So in this first example, we have one of these indeterminate powers of the type 1 to the infinity. So immediately we can evaluate this by rewriting it algebraically. And our technique was to think about it exactly how we would rewrite it in order to differentiate it. E to the 1 over 1 minus x, natural log of x. And recall, because the exponential is a continuous function, this limit can be pushed inside the exponential. So we would have e raised to the power of the limit as x approaches 1 from the right, and our exponent is natural log x divided by 1 minus x. And note in this case, I'm just going to keep it all together and evaluate it because I think it's going to work out fairly quickly and efficiently. As x approaches 1, natural log goes to 0. As x approaches 1 from the right, 1 minus x also goes to 0. So this limit can be evaluated using L'Hopital's rule. So we would have e raised to the limit as x approaches 1 from the right. We take the derivative in the top, and we divide by the derivative in the bottom. And now, as x approaches 1 from either side, 1 over x is continuous at 1, so we can simply substitute in 1. 1 divided by minus 1 is minus 1, and the value of this limit would be e raised to the minus 1. Moving on to our second limit, as x approaches infinity, what can we say about x e to the 1 over x minus x? Well, if we think about these things individually, as x goes to infinity, 1 over x is going to approach 0. And note, e to the 0, so that exponential term would approach 1. But as x goes to infinity, x is going to infinity, e to the 1 over x is going to 1. So infinity times 1 means we're going to infinity. So we have one of these indeterminate forms of type infinity minus infinity, which indicates algebraic manipulation is required before we can take this limit any further. In this case, the observation we can make algebraically is both terms involve an x. So if we pull out that x, we're left with an e to the 1 over x minus 1. And as x goes to infinity, x goes to infinity. And we just observed that e to the 1 over x is going to 1. which means this second term, e to the 1 over x minus 1, is approaching 0. And that indicates we are in a scenario where we can rewrite this again algebraically so that we can apply L'Hopital's rule. So I'm going to leave the e to the 1 over x minus 1 in the top, and multiplying by x is equivalent to dividing by 1 over x. The function in the top is going to 0, and the function in the bottom is going to 0. So L'Hopital's rule tells us that we can evaluate the limit where we take the derivative in the top, divide it by the derivative in the bottom. In the top, to differentiate e to the 1 over x, we need to use a chain rule. Derivative of the outside, evaluated at the inside, times the derivative of the inside. So the minus 1 over x squared in the top and the bottom cancel. And this works out quite nicely. We're left with the limit as x approaches infinity of e to the 1 over x. And note at this point, we've already explained that the value of that limit is going to be 1. But just to make sure it's as clear as possible, let me take this a step further. We can push the limit inside the continuous function. As x goes to infinity, 1 over x is going to 0. Remember, dividing by something big gives you back something small. So we have e to the 0, which is 1. Precisely what we explained earlier. And our final remaining limit is as x approaches 0 from the right of the quantity 1 minus 2x raised to the 1 over x. So note, 1 minus 2x is going to 1 as x approaches 0, and 1 over x is going to infinity. So we have an indeterminate form of type 1 to the infinity. So rewriting this algebraically, we have e to the 1 over x natural log of 1 minus 2x. Pushing that limit inside the exponential, and note hopefully this procedure is starting to feel a bit more efficient. And just while we're at it, going ahead and rewriting that exponent as a fraction, natural log of 1 minus 2x over x. This works out very nicely. As x goes to 0, the top goes to natural log of 1, which is 0, and the bottom goes to 0. So I'm just going to go ahead and evaluate this all together using L'Hopital's rule. This exponential function is going to come along for the ride at each step, and L'Hopital's rule applies to this limit. We take the derivative of the top, which requires the chain rule. The derivative of the outside, evaluated at the inside, multiplied by the derivative of the inside, and we divide by the derivative in the bottom. And just simplifying this a smidge algebraically, we can rewrite that as minus 2 over 1 minus 2x. And as x approaches 0, note the minus 2x term in the bottom approaches 0, whereas the minus 2 and then that first one in the bottom just stay at those constants. So the value of the limit is minus 2, which means the value of the original limit we were asked to evaluate is e raised to the minus 2. This completes our discussion of L'Hopital's rule, but as always, there are plenty of good suggested problems for you to practice. As you're working through and practicing, when you have questions, do not hesitate to reach out. Either drop me an email or stop by office hours. So stay tuned and take care.